Namaskar, Dineshji.
Namaskar, Amarji. Very nice to have you back. We'll wait a bit for the speaker to join us.
I thought I'll just listen to the talk about
Sure,
this
yeah.
wrapping design, see how it behaves.
Right, Dr. Garg. Warm greetings, Zdravko. Professor Terze is
Hello,
here with us right now.
Hello, Dinesh. Nice to see you.
Nice to see you too. I'm competing with your beard now.
Yes. Well, speaking of bird.
Good afternoon, Prof Terze.
So we have with us Dr. Amar Garg,
Yes.
Melbourne. So he was working in the aerostructures. He was doing composites research over there, all the way up to certification. So he has joined us for this talk. He delivers seasons of lectures on composites for our students. So that there's an ongoing series there, and he thought he'd enjoy this talk as well. Yes, Dr. Garg.
Yeah, I'm glad. I'm glad that this talk raised interest. It's fantastic.
True, true.
Yes.
There's a wide range of interest amongst the public in general, leave alone aerospace students.
Yes, I think it'll be interesting to me also. Let me see what's going on in the world now in aerospace. Although I've been long associated with aerospace. I was in Boeing for 32 years.
Yeah. Do you hear me? Do you hear me?
Very
well?
clearly, yes.
Yes,
Very
yes.
clearly. We can see your video also quite clearly.
Wonderful.
Maybe we can check with your presentation as well, just to make sure everything is in.
Yes. Well, then I should share a screen. Yes, probably. Let's see if does it make. Just a minute.
Sure.
Yeah, should be okay. Okay. Yes. So I believe you should see my screen
Yes.
now.
Yes, we can. Yeah.
Yes, we are.
Wonderful. Then this is great. Technology is working. Fantastic. Yeah. Okay.
We'll wait for a couple of minutes so that more people
Yes,
can
of course.
join. Yeah.
Of course. Of course. Of course. You just give me a sign when I should begin.
Sure. Yeah.
And so, Dinesh, how are you these days?
Doing very well.
Except
It's been a
for
long time
beard.
since we met.
Yes, indeed. This was in Rhodos, in Greece, right?
That's correct. Yeah. It's a lovely place.
Lovely place. This was the only time that I visited Rhodos. I haven't been there again.
I see. Okay.
Yeah.
It was a great time with your family as well. So I had a good fun going around the places there.
Yeah, I said to Irena, my spouse, that I will see Dinesh again, and she remembered our trip to Shimi, also the small island. It was fun.
Right. The ancient Greek churches and beaches are really amazing.
And quite interesting conference was that. It was mathematical conference,
That's
and
correct.
talk were quite late. I mean, you could have attended a talk at 10 p.m. something like that, as far as I remember.
Right.
It was insane. Yeah.
It's more typical of how research students work.
Yeah. Since then, I presented some talks on some other mathematical conferences, and these guys have quite a peculiar attitude. Sometimes they said, "Well, we prefer chalk and board. However, PowerPoint is allowed sometimes." So it's a different world, yeah.
The typical mathematician's way of looking at things.
Yes. So first time when you're exposed to that, you're a little bit So you are
have
in
a
Bangalore.
reasonable. Yeah, go ahead, Zdravko.
You are in Bangalore is the name of the
That's
city,
right.
right?
Yeah, that's correct. Yeah. So that's the anglicized version. The original name is Bengaluru, and
Yeah.
we've gone back to it officially about a decade back.
Yes.
Are you in
I'm
Zagreb?
in Zagreb, yes. I'm in Zagreb, and I must admit I've never been to India. This is
Oh,
something I have. Yes, it is something I have to fix.
yeah, that's a cardinal sin.
Cardinal Seal, yeah.
We will get that rectified. We have you here now virtually, so very soon we should have you in flesh and blood.
Yeah, but as you know, as long as we are here on Earth, these sins can be, improved, all right, or canceled, or whatever.
True, absolutely.
Redeemed, right? This is right. Yeah.
True.
Yeah.
So I think we have a reasonable number of people. Maybe I'll just give a brief introduction and then you can go ahead, Zdravko.
Okay.
So it's a very interesting talk that we have in front of us. Thanks to all of you in the audience for being here this afternoon, middle of the week. And as you know, unlike the Indian approach, which is typically holistic, the Western approach has always been compartmentalized, be it in medicine or any other sciences or technologies. And so it is in aerospace engineering as well. When the Wright brothers wanted flight to happen, they bifurcated propulsion and aerodynamics. So essentially, the lift generation and the thrust generation were bifurcated. Whereas what nature had taught us, at least on planet Earth, is that both of these can be arrived at from the same source, namely the flapping of the wing, both in the bird flight as well as the even lower Reynolds number of the insect flight. Of course, with engines for the thrust and the wings for the lift, we could achieve many things which birds and insects could not achieve in terms of speed and size, for that matter, scaling essentially. But when you look at certain more cutting edge and more demanding tasks, like what our friend Professor Terze is looking at, in terms of planetary exploration, where you're looking at thin rarefied atmospheres of Mars or very dense atmospheres like Venus, etc., then you do need to look at how nature has done it, at least on Earth, and see if something based on that can be extrapolated to how we can do it on these other planets. So a very interesting talk ahead. And knowing Zdravko, he would like this to be interactive. So I've, in addition to the chat that you see on the top of your window, I've also activated the Q&A, which should come up. If it's not visible, I'll bring that up as well. Otherwise, you can post your questions on chat. I've also enabled the microphones for all of you in the audience as well. So whenever you have a question, feel free to stop and ask the question, especially if you think it helps the other rest of the audience understand the talk better. Otherwise, you could wait till the end of the talk and then ask your question. So let me give a briefing about our speaker, Zdravko. He's a professor, a full professor at the University of Zagreb in Croatia. He's the head of the study of aerospace engineering. He's also the head of the chair of flight vehicle dynamics, the purview of which this talk typically comes. This is as part of the Faculty of Mechanical Engineering and Naval Architecture. Quite some time back in 1996, he received his PhD from the University of Zagreb. So he's a inbred student of Zagreb, becoming a faculty over there, as is the case with many of his generation and prior to that around the world. So as an invited scientist, Zdravko pursued his research in the domain of computational mechanics and multi-body systems dynamics at two universities, the universities of Brussels and Stuttgart. And he was also affiliated with the Schlumberger in Vienna, Austria. He's also an adjunct professor at the State Key Lab of Robotics and Systems at Harbin Institute of Technology in China. He delivers both undergrad and postgrad courses at the university where he works at Zagreb, and has delivered lectures and seminars at renowned institutions around the world like Caltech, also NASA JPL, Politecnico di Milano, with which I also have a long association, University of Stuttgart, ETH Zurich, UPM Madrid, as I mentioned already, Harbin in Beijing, also Harbin, and apart from Harbin, Beijing University, known in short as Beihang, as some of you would know, and a number of international doctoral schools as well, which specialize in research, such as École de Physique de Hauches at Les Hauches in France, and the International Center for Mechanical Sciences in Udine, Italy, and Colloque International de Theories and Variationals, France, should be of great interest to many of our labs research students, because we work primarily on the variational asymptotic method. Professor Terze was appointed an expert member of the European Commission's expert group on space surveillance and tracking, SST, in the years 2014 to 21, included the COVID years as well. He was appointed member of the European Commission expert group on governmental satellite communications. Since 2021, more recently, he has been an expert consultant in the program called Support Services for EU Space Programs. The EU Agency for Space Program handles that. As a PI and head of research, Professor Terze conducted many research programs supported by the European Space Agency, NSF, EU research funds, and industrial partners in the domains of mathematical and numerical modeling, nonlinear multibody dynamics, space robotics, autonomous systems, computational multiphysics, and of course, the current trending AI. He has published more than 140 scientific papers in international journals and conference proceedings, and served as the scientific chair of the specialized symposia in the field of computational dynamics and simulation methods, held within some distinguished international scientific conferences, such as the ASME, ECOMAS, IUTAM, GAM, etc. Many of you working in the field will be familiar with these leading conferences in this particular area. Professor Terze was also the co-chair of ASME's 13th and 14th International Conference on Multibody Systems, Nonlinear Dynamics in Cleveland, USA 2017, as well as Quebec City, Canada 2018. Furthermore, Professor Terze serves as a reviewer of international scientific projects for several national scientific agencies or foundations. He's a member of the ASME Technical Committee, TC, on multibody systems and nonlinear dynamics, and a member of the advisory board of the scientific journals Multibody System Dynamics, which is Q1, Aerotechnica, Missili, and Spaceo, is a journal of aerospace science, technologies and systems by Springer. Professor Terze also served as an associate editor of the ASME Journal of Computational and Nonlinear Dynamics in the years 2014 to 2020. He was elected the vice president of the Croatian Academy of Engineering Sciences. He served in this position from 2013 to 2022 for an entire decade and has received multiple awards for his academic work. So we have a very illustrious speaker with us and a very, very friendly one at that, a rare combination. So the platform is yours, Zdravko.
Dinesh, thank you very much indeed for this very nice introduction. And especially beginning, you gave a nice perspective comparing this traditional and flapping wing kind of thinking, holistic and all those. Actually, I'm completely on your Indian side, although I'm coming from more from the West. I think that this holistic approach is one to go, and I hope that we did some steps ahead along that line, and some of these things I will be talking to you.
That's really wonderful, Zdravko, because I think being in Croatia, Eastern Europe, you're like at the interface between the West and the East. So you have a very good understanding of both, and you can see the pros and cons of both these methodologies or approaches.
Yes, I could agree with that. Well, people here try to have the frame of mind that we are belonging to the West, and probably this is the true. However, I like to say that I'm citizen of the world. I really enjoy both sides. So I do not have preferences really. I think that we should combine things. Okay, going back to the subject. Now I will put my presentation on. I hope you see the thing. Yeah, is it? Do you see it now? My screen.
We can see your screen, but not yet the presentation.
So it should be presentation now on the screen. Just a minute. Because it's written now. I'm changing slides. You don't see those things?
No, we just see your folders.
All right, something's then. Just a minute.
Sure.
Just a minute, because it should be. I will share it again.
Okay.
I will share it again. Okay. I will okay. Okay.
It's like he got disconnected. Very short presentation indeed. Let me try to reach him.
So here I am again. Do you hear me?
Yes, Zdravko, welcome back. We can see you and hear you as well. But
wonderful. Okay, now I hope things will work. All right. Do you see my presentation now?
Yes, we can. Yeah. Yeah. Is it possible to
Wonderful.
get into the presentation mode?
Yes, of course. Okay.
Yeah, perfect.
Works now. Fantastic. So my talk, the title of the talk is Flapping Wing Propulsion from Space Exploration Perspective. I'm coming from Zagreb, as Danish have said already. So let's take off. Before I start my main topic, and this is of course flapping wing, and this extraterrestrial context. Probably before that, we should say a few words. Why should we fly on those planets? Because as we all know, we do have also rovers. We have rovers as a civilization. Let's say we have rovers on Mars. We have rovers on Moon. And those machines are, let's say, successful. However, they do have drawbacks. For example, if you take a look on a Curiosity rover that is still alive, it's a NASA rover from 2012 up to now. 20 kilometers is approximately distance this rover has traveled in this period from 2012 to up to the present. So 20 kilometers is really not a quite long distance, and similar data you can find for other rovers. Opportunity rover has a record for 45 kilometers, but for 14 years, duration of 14 years, and let's say two of most recent ones. Is Zhurong, a Chinese rover on Mars. In 358 sols, traveled less than 2 kilometers. So these guys do not travel very fast. And for example, Perseverance, it's the newest, the last NASA rover. Top speed is 0.15 kilometer per hour. It's not a wild ride, indeed. Of course, terrain on Mars is Moon is different, but also similar thing. Terrain on Mars is quite rough. You have a combination of sand and rocks, and this means that those wheels can be damaged, and those machines can sink into the sand. I am also collaborating with a Chinese colleagues on the design of those rover systems. So I can really tell you it is a challenging thing to get these guys going as you expect them to go. And of course, damages can occur. For example, these photos I made by myself. I was invited to give a talk in a jet propulsion lab at Caltech a few years back, and during that occasion, I made a photo of myself. It's a Curiosity rover, and it's a replica. However, well, one very realistic replica, and you can see those damages here as well. So, of course, if we could fly, then we can avoid many of those problems. And along this line, most recently, two missions successfully put rovers on Mars. It's a year 2021. So one of those is a Mars mission, NASA. So they landed the Perseverance rover, and two technologies were in focus for them. One of them is an Ingenuity helicopter. So this is the first time that we, as a civilization, let's say, made successful powered flight, extraterrestrial flight. And this helicopter, now I should go to another slide. Yes, it's here. So this is the first powered extraterrestrial flight, Ingenuity helicopter. Maiden flight was April 19, 2021. And as probably you follow the story, it was a successful project. However, quite very recently, the helicopter suffered some damages. It's not alive anymore, but it has proven that this kind of flight can be achieved. Well, NASA has chosen to fly there by helicopter technology. And this is because one of the reasons can be that, as you might know, and Dinesh, you know this very well, since you were on a Georgia Tech, and Americans are very skillful and very well known for building of helicopters. So this is a really top expertise. So knowing that, probably they have chosen a helicopter because they know this technology very well. So they scaled it. So they modified to allow this flight on Mars. However, this is quite challenging because of different things. But I will now focus on the main point. And the main point is that atmospheric density on Mars is 1% of the density here on Earth. Okay, we also have a different chemical composition. It's a 95% carbon dioxide. There are some other also very harsh temperature range. But let's focus now on let's say on aerodynamics. So 1% of density, it's a challenge. And this means that you need to fly on a very low Reynolds numbers. As you are aerospace guys, you know very well what does it mean. Mean that general aviation, we have 10 power 6. A Mars helicopter, that one particular one is 10 power 4. We calculated that. However, if you want to have another vehicles there, probably smaller ones, or you need to go below this. And now you have a problem of flying in the low Reynolds numbers. Well, if you want to use a helicopter, as NASA successfully proved it's possible, it is possible, but the question is it really the best way to go? Because in the low Reynolds numbers, rotor wings are not a ratio between lift and drag deteriorates significantly in a low Reynolds number regime. In a conventional thing, conventional situations, you have a good ratio, but when you go to small Reynolds number, the rotary wings are not efficient anymore. This also has a significance. We all know this quadrotor, these drones flying around, delivering pizza, whatever. They are everywhere. However, if you want to scale down these quadrotors, then these guys start to be quite noisy and quite inefficient, because rotary wing is not the best performing wing for smaller Reynolds numbers. However, if we take a look in a holistic approach, as Dinesh said, or if we take a look what nature has to offer, and we should do that, of course, then you will see that for this kind of flights, nature came up with the flapping flight. And flapping flight is a not new invention. It's 350 million years. You can see this fossil. So this is something that nature knows for a long time, and we still need to learn it. So we are not very good students. However, let's try to improve the whole thing. And now I will be able to give you some more proofs. For example, there are different diagrams saying that if you are using flapping wing in a lower regime, you can achieve better lift, or you consume less power comparing to rotary wing. So there are different investigations on that topic. And now I will quote one paragraph from one paper. Flapping wing propulsion under drive of the same motor can be up to 40% more energy efficient than propulsion with rotating propellers. Of course, this is not axiom or theorem. It's not valid everywhere. However, this is something that we should consider really as a fact. So it all depends on the situation, but flapping wing does have advantage. You will see a little bit later some other things. For example, already in this slide, it's not only that you are efficient, but by using flapping wing, as our small friends showing us now is a spring here in Croatia. I can take a look in my garden, and you can see those small guys flying around really skillfully, really amazing what they can do in the context of maneuverability. Also, those wings are mostly flexible. They should be flexible, meaning they're robust. If you hit obstacle, nothing dramatically should happen. And also a very important thing that okay, this is also has to do something with control. It's not only aerodynamics, but control is also a very important issue. You can adapt quite nicely if you have a gusts. So flapping wing is something very interesting. Well, if one ask himself or herself why this happens, so this happens, I mean, all this flapping idea, it's a completely different aerodynamics comparing to our conventional aerodynamics, because when we teach our students, we start with the flight mechanics, and so we aerodynamics. Then we mostly focused on a stationary aerodynamics. However, insects they take advantage of unsteady flows. Please understand that birds and insects do not fly in the same way. Birds fly, well, there are some they do have flaps, of course, flapping, of course. However, they need a horizontal velocity. You remember those big birds? They need to have some kind of acceleration before they start to fly. They need forward velocity, similar as our fixed wings designs. However, insects can hover. Okay, there is this small bird that can also hover. However, this is a speciality of insects. And how do they achieve? Well, the complete physics, how do achieve this very very maneuverable and very efficient flight? We do not understand the whole physics completely. However, now we do understand a lot of things, and one of those very special mechanisms is so-called leading edge vortex. For example, if you take a look in this video, you see that flow and the leading edge is quite chaotic. However, in the case of the flapping in a flapping wing, you will see it in a minute. You will see that this leading edge flow is not that chaotic, so it follows geometry of the wing. So exploring this leading edge vortex, it's important feature. Of course, it's not only this. This flow is quite complicated. You have different details here. I cannot go of course to many of those. I just emphasize the leading one. I mean, the main one, this leading edge, and this leading edge vortex. Actually, we understood that's not that far in the history. It's a quite recent insight. Speaking of this, it is paper published in, I think, Science or Nature, where people studied it was this bumblebee, I think it was. So it's a quite famous paper, and actually they recognize this leading edge thing. However, as I said, it's a cocktail of different vortices, and what is important to understand. Unlike our principle, we have a fixed wing, and we have those vortex wake that we leave behind, and we leave a lot of energy behind, and we made chaos behind us. these guys actually harvest vortices in the ambiental fluid, and they take energy from ambiental fluid, and they propel themselves really cleverly. However, it's not only about it's not only in air. If you go to the aqua fluid, you can see the similar phenomena. For example, tuna, it's very quick fish, and they also explore this leading edge mechanism, so unsteadiness. There is one creepy, quite bizarre experiment that is, you can find it in literature, that the researchers found out that actually a dead trout can swim upstream just harvesting vortices in the ambiental flow. So it is very interesting idea. So if we have a flexible wings, flexible bodies, then we exchange energy with the ambiental fluid, and we take this as this energy for our own purpose. This is, I think, very nice principle. It is also quite interesting that if you take a look at the Strohal number for these fish guys and those flying organisms, actually the Strohal number for optimal propulsion in both cases are in a quite similar range. Although we have air and water, different fluids, Strohal number for optimal propulsion is somewhere in the same range. We use this for our numerical procedures, this experimentally observed facts. However, this is some kind of symmetry in nature, which is very interesting one and not very well understood so far. Okay, now I mentioned this aqua animals for purpose because we focused our research not only on Mars but also on Venus. And if you go to Venus, Venus is really strange planet. I could use another 15 minutes to speak about really weird things going on up to the Venus. However, we don't have a time for that now, but now I will only emphasize that we have a different situation now. Now we have a thick fluid. Surface pressure is 92 bars, and we have a 67. I mean, you see this these two numbers, so it's a much thicker atmosphere than on Earth. Chemical composition is quite similar to Mars. However, there we have a thick atmosphere here. So if you want to fly to Venus, you have somewhere between the swimming and flying, because you have a different density. Now you have a thick one. However, as I mentioned here, that flapping wing can be successful in a much more dense fluid. We have idea. Okay, let's go for flapping there on Venus as well, because we have inspiration here on planet Earth. We published a paper in Acta Astronautica on that. I think it's the first paper ever approaching this phenomena from this perspective. So now we are building also these things. We are doing research in Venus as well. However, this talk will be focused more on Mars, because Mars is now a focus of many agencies, space agencies. Recently, actually, I learned that also India, you guys also have ambition to go to Mars. So good luck with them. Probably this talk also will give you some, well, let's say, inspiration for some, when you come there, what to do there, right? So, but let's go back to the Venus for a minute. So if you go to the 50 kilometers height, then the situation is ideal, very similar like in Earth. You have a pressure and you have temperature similar like Earth. So on 50 kilometers, you have a well, nice, mostly good condition. Vehicles that are designed to fly on Venus, they're designed to fly on a higher heights, 50 kilometers, because, as I said, it's a ideal situation from our Earth perspective. And also, you have we have sun for a good for a long period because Venus is rotating very, very slowly. So you have a sunshine, you have a daylight almost. I mean, it's 3 months or so. So it's a very good situation for your solar panels. However, on this altitudes, you have a very, very heavy winds because Venusian atmosphere have this super rotation. Nobody knows actually how that happens because it goes very, very, it rotates very, very violently, and planet rotates slowly, in slow fashion, slow manner. So it's a quite interesting situation. And you have this very wild winds there. So those balloons actually didn't have a quite comfortable flight there. And our goal is to design a vehicle that will fly around the vicinity, not in a 50 kilometers, but in the vicinity. There it's good because we don't have a winds anymore. However, you have very hot situation, almost 500 degrees Celsius, and pressure, as I already mentioned. However, we do have technology that we can cope with those things. For example, during the last period, let's say last few decades, there are this number of successful missions on Venus. In Venus, mainly Soviet Union, they landed a number of probes, but this is just a probe, just a probe, and they got some signals. So we do have electronics that can sustain these harsh conditions. However, we would like to also to prepare ourselves to fly there, right, or swim. Probably more flying, but it's a thick atmosphere. Well, just to mention that actually on Venus 1985 we did have a first extraterrestrial flight because NASA, sometimes in the media, they said that when this Ingenuity helicopter made takeoff, that this was the first flight ever. This is not true. First flight was on a Venus, but only balloon, so it was static without power. So Ingenuity helicopter is first power flight, not first flight ever, but first power flight. Okay, now this is the context, and I will now proceed with the designing aspects of Mars and Venus flapping flight vehicles. I will, in the rest of my talk, focus on Mars. The same ideas, the same principles can be used also for Venus. As I said, we published a paper on that, and a lot of things we can use. I mean, for both cases, but since Mars is really focus of many agencies, I will proceed with the Mars in my focus. Speaking of agencies, NASA is already there. Chinese, they do have a rover over there, and this particular research that I will present right now, in my case, was to the bigger extent funded by European Space Agency. So actually these are results of the project we conducted for them. I was a principal investigator, and I did have a subcontractors, TU Delft and Politecnico di Milano. Divinity also knows these guys very well, so they were, Politecnico di Milano were also a subcontractor on this project. I was a principal investigator. We finished this project very successfully. Now we propose the follow-up, but let's talk about these things later. So now let's go what we should have in, how should we design those flight vehicles, and of course we should start with atmospheres. Before that, just to give you an idea, what we want to do, we actually designed the optimization procedure because probably some of you did some experience, did have some experiments, and do have some experience with the flapping wings. So in nowadays, in flapping wing designs, what people people mostly do these things experimentally. Or if they use numerics, CFD or FEM, finite elements, fluid structure interaction, they do this case by case. Because they use high fidelity numerics, so which is time consuming. Then you establish the model, then you run the model, and then you see how it works. Then you tune things, and then you go again and again. And we didn't want to do that. We wanted to come up with a optimization procedure where we can put everything inside a solver and optimize things and see what happens. So idea was, let's choose the main inputs, location of the planet, because it is important, because of density is changing. So you choose your velocity, you choose your mass, you choose your fuselage size. This is important for Venus because you have a thick atmosphere, and with a more, if you inflate your fuselage, you can even achieve buoyancy. So fuselage size was important for Venus, not for Mars. You have your wing mass, you estimate, and then you put this, you feed those data in the optimization procedure, and our optimizator core is a fluid structure interaction, as you will see in a minute. Now not high fidelity, because you cannot do it in high fidelity. We have reduced other models, and then you choose your initial parameters, and then your optimizer gives you the two most important things. First is, or three, wing size, and of course frequency of flapping, because these two things influence each other. So you can have a bigger wing in a smaller frequency, or a higher frequency and a smaller wing. So you have to decide what you should do. And very important, our optimizer also gives us a flapping pattern, because in the flapping wings, it's very important how actually you move your wing. All of those small friends, insects, every guy has some own trick how to do a flapping, and this trajectories, these kinematics can be quite complex to achieve this unsteady effect to harvest this energy and to propel itself in an efficient way as far as it gets, right? So it's very important. Now you got your initial data, and then your optimizer gives you these three things: wing size, frequency, and flapping pattern. Of course, you do not have one solution. You have a numbers of solutions, and then you choose which one you would like to go for based on other criteria, structural design criteria, etc., etc. Okay, so let's go back to atmospheres. We obtain data from Venus, we obtain data from Mars via European Space Agency. So people know these things, right? They have measurements, and we really have those data ready to use. So this one we obtained from France for laboratory météorologie dynamique. We obtained via European Space Agency. So you see, in Venus, you have homogeneous situation because you have a thick clouds and everything is dense there, and everything is quite hot and not changing in geographical manner. So however, this is the truth. However, in our case, we have chosen the two positions because of the height, geographical height. You can find this atmospheric density is changing, not very much, but it's changing. So we consider the two positions in the Venus. You can see this different probes from previous missions. So actually, in our calculations, we use the density from these two locations to feed in our optimization process. Well, now I'm going to Mars. Mars will be, as I said, my main topic. In Mars situation, you have a much more diverse, not that homogeneous situation, because Mars has inclined axis, Mars has a rotation, Mars has seasons like Earth, so things are quite changing there. And you see density profile is also quite different based on a position where you put yourself on Mars, meaning that in our case, we selected 3 locations. We negotiated with the European Space Agency because Europe we did have also plans to put rover on Mars. However, due to this conflict in Ukraine, this project was cancelled. So but the plan was there. Even rover was designed, so we also used some data considering this planned site. However, we also have chosen 3 other positions because density really changes, you see. So if you want to fly on these 3 different positions, it's not the same, not the same case. Okay, these are different positions from Pars. You see Perseverance. This is Zhurong. Those guys were landed to 2021. The newest rovers, and Curiosity I think is still alive. So those things are ongoing. Okay, now I will change. I will proceed with some mathematics and models and optimization with a Mars and a focus. So when we designed our solvers, we had two main, let's say, approaches. And the first one is based on, both are based on geometric mechanics insights. However, first one is a really fluid structure interaction. Another one is a quasi-steady solution. So I will first talk on this fluid structure interaction model. So it is we started from geometric mechanics. What does it mean? This means that we do not live in vector spaces anymore. So we don't have vector spaces, we do have manifolds. Manifolds and special manifolds called Lie groups. Okay. So why you do this? Because this is the kind of mathematics that normally you do not have in let's say, basic engineering curricula. So it's a little bit more, let's say, abstract. So why go to this curved spaces? Because those spaces are curved, not linear vector spaces anymore. Well, there are different reasons for that, and when I give a talk on that, I can give a let's say whole course on the topic. Of course, now I'll just have a good basic ideas. So there is a traditional link between analytical mechanics and differential geometry. You can think about this brachistron. You can think of this shortens paths between the 2 points, etc., etc. There are different stories. We know them very well. However, in our programs, in our codes, multibody, but this is not only multibody. Those things are also very important in the finite elements and also in the CFD. Well, 2 things actually are very important. This is how do you actually cope with the 3D rotations. It's a so-called nonlinearity, of course, because finite rotations are not vectors quantities. So you have to deal with this is geometrical nonlinearity, as we call it, right? So how do you deal with the 3D rotations, finite rotations, and how do you treat your configuration constraint? These 2 are very important issues in multibody dynamics, but also in finite elements, and also in a fluid case. Because when you have a incompressible fluid, you have divergence-free flow. I will mention that a little bit later. This is also a constraint. So this is also a constraint. Actually, it's also DAE problem, differential algebraic problem for index 2. Here in a multibody, we have index 3, which is a little bit more complicated, but nevertheless, treating 3D rotations, finite rotations. It's a nonlinear process, and how to treat configuration constraints, it's a very important issue. Also, in learning processes, we have the geometrical ideas implemented in the artificial intelligence, deep learning algorithms. I'm involved in these researches as well, and but this is another topic. So all these two very important issues, they call naturally for geometric mathematical framework, because when you live in the manifolds, you live in the nonlinear spaces per se. So you don't need to. So if you can configure your covariant space cleverly, then you can go along constraints. You do not push constraints. So it's a very interesting ideas. And to cope with these ideas, you need to have a little bit more mathematical angel to understand what's going on. So this is the let's say main point why adopt this geometric mechanics tool power, let's say, right? Based on this, you can design a smart integration procedure. The ones that will go along constraints, they will not work against constraints, but along constraints. You preserve kinematical constraints. You preserve dynamical constraints, because, for example, if you fly if you have a satellite, you have a more or less a free body. This means that angular momentum is conserved. This is dynamical constraint. So you can design your mathematical integration tool that will preserve numeric angular momentum by definition, or preserve energy by definition. You cannot do that by using traditional integration scheme. They will violate those constraints, in a few steps. So therefore, if you go for the Lie groups, you might find a good smart way how to do these things. We publish some papers, so if somebody is interested in that, I can provide more information. And what is very, very important is when you design reduced order modeling, because models, which is very important, as you know, in artificial intelligence, to reduce big data, to find symmetries, then to reduce model by using this system symmetries. This is a really powerful thing if you can do that. And these symmetries are visible from this Lie group's point of view. And I also use the symmetries in my research when I design this monolithic coupled fluid structure table. I will proceed in a minute. Well, of course, people say multiphysics. Multiphysics does not exist. Remember, Dinesh, from a holistic approach, we have one physics. So we have this multiphysics idea because we divide this physics in a different, by treating fluids, by treating solids in different manner, but those guys actually belong to the same universe and to the same physics. And if you use this geometrical approach, then you can find those similarities and use symmetries. This is very, very important. This not only holds for fluids and solids, it also tells this similar stories in optics, in magnetism. It's really fantastic. When you go to these things, when you understand how physics works and how things are similar in different domains, it's amazing. This planet is really amazing, or universe. Okay, so let's go back to the Earth. What we need to do in aerospace, we have a wing or whatever that propels itself through the fluid. And what is the conventional way of doing these things? To fluid structure, normally you discretize your fluid with finite volumes. You can use finite elements, whatever. So you discretize the whole continuum of your or the big domain of your fluid, and you have your solid. You have one solver for fluids, you have another solver for solid, and you hope that these guys are talk to each other in a nice manner. But however, sometimes they do not talk as you expect. You have instabilities. If you have a large motions, you need to have a alley approach. You have to need moving meshes, and this is another problem. Of course, people are doing this for decades now. They understand this approach. They have a very, very, very good results, of course. And all modern airplanes are actually designed by using this kind of technology. I do not criticize it. I just emphasize that this is a problem. There are some problems inside when you divide those things in two domains, and especially if you have a flapping wings, which is our case, then we have a complicated we have a complicated kinematic. So we don't have just a flutter, let's say. We have a very large movement of the wings, meaning that you need to move your meshes very you know, to a large extent, and this gives a problem in the stability and the energy transfer between the two meshes, etc., etc. Okay, there are some meshless methods. We know some of them. However, they do have some problems on their own side. So just one sentence in very many occasions, and this is my position. Actually, I'm mostly interested how this ambient fluid influences solid motion. I'm not that much interested how does this wake propagate itself in the fluid? What does fluid do? I'm interested mainly how fluid influence my solid motion. This is my focus, and it would be wonderful if I would be able to reduce the whole fluid only onto the solid, so without having necessity to discretize the whole continuum to get this information. Of course, it's a question that can we do that? And yes, we can, because and then we come again to the geometric framework, because rigid bodies, I'm speaking with the rigid bodies now. However, we can extend this idea to flexible bodies straightforwardly. And fluids, they do have the same mathematical framework, so-called Lie groups. So rigid body movement lives on a special Euclidean group as a rigid body movement, or you can have a rotation and a translation. SO3 is rotation group. You have this is just ordinary translation, vectorial translation. So you have a Lie group on a solid side, and you have a Lie group on a fluid side. It's so-called volume-preserving diffeomorphism. So both guys live in the same mathematical concept. So you can reduce it. You can treat it all together, right? This is the main idea. Treat the things all together. Okay. Going back to the MAU model, I have 2 wings. Sometimes I have 4 wings. It's a multi-body model by definition. So you have your state space, you have a rotations of each body, and you have a tangent bundle. I will skip these geometrical things right now. And so, but idea, the basic, what is important, we leave on the Lie group here. And also incompressible ideal fluid. I start with the ideal fluid. After that, I will introduce some vortices and circulations. I start from the ideal fluid. It's a Lie group. It's a volume preserving diffeomorphism. This is actually position of the fluid particles, right? So what is important here for just to understand the one idea I would like to emphasize is that actually you have Eulerian velocity field, and this Eulerian velocity field is invariant, is intact if we put another set of particles in the beginning of our process. It's so-called particle labeling symmetry. So if we put another set of particles in the beginning, this will not change Eulerian velocity field in our domain. It will not change kinetic energy of our fluid. This means that this symmetry can be used for reductions. Okay, and this will be done all together. I have a Lie group. I have a multi-body system in ambiental fluid, which is Lie group. I have a fluid. This is Lie group. Then I can act. We call it act from a right with a Lie group diffeomorphismal fluid, and by this action, actually, I reduce out my fluid positions. And at the end of the story, I end up describing mathematically the whole system, fluid and solid, all together only by solid variables. So fluid is reduced out from this picture Of course, it's not a magic. It's still there, but only via added mass phenomena. So actually, a fluid is influence of the fluid to the solid motion is incorporated in added mass phenomena. So what I have now, I have a solid multi-body positions, orientations, velocities, accelerations, and however, inertias of these bodies now have a added inertia because the whole thing is not in vacuum but moving in a fluid. Okay, what I have achieved now, I achieved this, that instead of having, this is, for example, the picture of the meshes, because we did, of course, also standard approach by having, we did this by combining open foam and MBDyne, two softwares, MBDyne for a multi-body for a body, foam for a fluid, and because you have a very large movement of the fluid, you need to have 1, 2, 3, 4, 5 meshes, and so you really have to invest a lot of computation to calculate your fluid. And in the story, what you are mainly interested in is only solid. So you really have put a lot of effort for the information you are not that much interested in. So with this reduced approach, you need numerics again. Why? Because your configuration, because I have a multi-body system, my geometric is changing in a fluid. However, I can reduce this finite volume or finite element approach for a continuum to discrete elements. What I need to discrete only boundaries of, so it's a boundary element method, BEM, right? So what I need to do is to discretize only counters of a solids, and I do not need to discretize the whole fluid domain, which means I have a reduction by several orders of magnitudes in this approach. This is not high fidelity approach. I cannot have a turbulences and a fancy thing, for example, large eddies, etc. However, I can extract basic information which actually I need for my optimization purposes, right? So it's of course, it's always a price you have to pay. You cannot by this you cannot have everything. But if you want to have information how my solid is moving, then you can do this, and this is efficient enough to be put in the big optimizer, which actually gives you this data, gives you information, coupled information. You don't need to start every time the new simulation, changing things by hand, launch it again, wait for a few hours sometimes because it's unsteady, it's complicated. Of course, it depends on your hardware, but it's a time-consuming process. You put it inside of an optimizer, you get your coupled system optimization results. So it's really a benefit. At the end of the story, we end up with this kind of matrices. It's a standard for multi-body system. Since we are living in Lie groups, we use also a geometry integrator. It's a multicast. Multicast is, you can think of it as a Runge-Kutta, but on a manifold, on a Lie group. I also published some paper in this domain, how to treat multicast in differential algebraic equations. These are you see this constraint. These are constraint matrices. You have a constraints. You see, because you have these joints. So you need to treat those guys, and then you need to solve it by incorporating constraints. But we have our setting to do this on Lie groups. Well, another simpler approach is a quasi-steady model. It's a quasi-steady. It's based on experimental results. It's a very nice for flapping wings because people did some experiments and they came up with let's say magic formulas for flapping wings by considering 2 or 3 degrees of freedom for these wings. So if you keep your physics around the numbers that are used for these experiments, then you can really have a good results with this. So you should use it, and we did use it. We had a good experience with those formulas. Again, you have to use it how they are designed, because they are based on experiments. So if you change a lot of things, then of course you cannot expect that your physics will be right. But if you stick with your experiments, then things can be quite nice. At the end of the story, we put everything in the optimizer. We design it based on the discrete mechanic optimal control DMOC procedure. It's also designed on a manifolds. Basically, you have your criteria. Our criteria is to minimize energy, and then you have your setup motion equations and the constraints. And then you are searching for optimal wing pattern, optimal, of course, and wing size and frequency, but also a wing pattern to minimize your energy for this kind of for this kind of task. Mainly, we focus on hovering, but you can also have a forward flight. It depends how you set up your optimization process. First, what we did, we tested our procedures by calculating two flapping systems that are very well known here on Earth. They are our friends from TU Delft. They were subcontractors here on this project. They actually came up with a very successful so-called dēvō. dēvō probably is the most versatile flapping system built up to now. However, here we tested these two guys because they had two wings, and the dēvō has 4 wings. So this is but okay, this is not a point right now. So we use the two famous flapping systems, and we tested. We feed in data from those systems and to see how our optimizer would treat the cases. And actually, we really obtained a fantastic, I would say, or very good, whatever, how you call it, matching. You see, this is what is the reality, and we have a very good match with our optimizer, also for a RoboBee, also for a Hummingbird. This is American design. So we achieved a quite good match, and with this we got a confidence that we're doing a good job, and we can proceed. And what we proceeded, we go to Mars. All right. It's published in several papers in molecular dynamics, in aerospace science and technology. So idea was, this was how we started. Idea was, let's take one flying system and we use a fruit fly. This is a fruit fly, and let's enlarge these wings for a Mars condition. But by using fruit fly physics. Why? Because with this magic formula, quasi-steady formula, were designed for fruit flies, right? So we could have used this fruit fly magic formulas to feed in our optimizer, and we also use our reduced model. But we try different things. But we could have some things to some criteria to compare our results against. Right, so we feed in this optimizer. So we changing the scaling number. What wing size we should have for optimal flap on Mars. Changing Reynolds numbers, meaning changing flapping frequencies, and then you get of course, set of solutions. Those dark green are optimized. So then you can choose which one you want to have, considering some other criteria, engineering ones, etc. Of course, there are very many. These are 10,400 optimization cases, but actually we did much more. So you need to have optimizer for that. So it's a big difference. Normally, if you don't have optimization process, for each of this point you need to launch a separate simulation to blah blah. Now we feed in everything in optimizer. We have this reduced model or a quasi-steady, and we end up with the optimized flappers. So we have idea if you want to build a flapping machine on Mars, where you should start from. All right, which kind of size of the wing, which kind of flapping, you have idea. You do not have, you start from somewhere. Okay, of course, for detailed design, you need to go further into the depth. But here you have a basic idea where you should start from. Okay, for different concepts, you have a different geometries, flapping geometries. For example, two angles. We have a stroke angle and a pitch angle. These are two angles, main angles for flapping purposes. So we are varying those, and you can see this how they look like for various combinations. And also you see that you can use different masses. We change from 50 grams to 750 grams. So you change your masses, and you see that you can sustain your flight in different regimes for different frequencies, different wing lengths. These are all optimized flight. If you, for example, if you focus on one mass, 250 grams, for example, then you see that you can have a hover, optimized hover for larger wings and smaller frequencies, or for smaller wings and large frequencies. However, our optimization procedure gave us result that actually more efficient, less power you are using with a larger wing and a smaller frequency than with a smaller wings and a higher frequency. So you should actually design your point around here, not around here, because you consume less power, right? For this, then this is for two positions on Mars, Oxyaplanum and Siriaplanum, depends on a density. So you need to have all these things, I mean, somewhere in your process, because density is changing. Well, then speaking with our colleagues in Delft, they do have this experience building machines, Delphi I mentioned already. You can see Delphi on YouTube. If you just write down Delphi, you see it's quite a nice machine, quite well designed, and they actually have a company producing these drones, and the flapping drones. It's quite attractive thing to see. These guys told us, Professor De Kroon told me, well, yeah, it's nice you can hover, but you need to have extra power for maneuverability, for a control, at least 20% extra power to above your hovering efficiency. So then we try, let's say, okay, now let's see what can we, what is the weight we can lift with the flapping wings. And actually we obtained very good results. For example, 7 kilos or 4 kilos. So it's a quite high masses you can lift with the flapping wing, meaning that you have this excess power. If you have a lighter machine, you have excessive power for doing another performances. Meaning that again, flapping wing proved to be quite capable technology. And the last point, and I go toward the end of my talk. However, what is very important for a flapping wing is this efficiency again, but not only from the point of view of aerodynamics. I mentioned that for an aerodynamical point of view, this flapping wing should be more efficient for low angles than a rotary wing, for example. But not only for this. What is important is that you can use a passive dynamics. You can use your elasticity of your system to diminish this total power consumption. Why is it so? Because you have repetitive motion. Meaning, if you design your elasticity of your system wisely, then you can use power, use from one part of cycle compression, and then release it in another part of cycle. Meaning you can have a in your system you can save your energy. And as you know, all successful, let's say, successful animals they do have this passive dynamics very well tuned. For running, for example, you can think of kangaroo or a gepard, or also flying. Our interest in flying organisms, they have this elasticity very well tuned, and wow, this they change, they conserve energy. And so we also play the game. In our optimizer, we put a different set of springs in our system, and actually what we have achieved is that we emulate more or less completely energy that is used for inertial forces. And this is especially important for Mars. It's also important here on Earth, but especially in Mars, because in Mars you have a thin atmosphere, because dominant forces is actually coming from inertial forces. And if you have your smart tuned elasticity, you can conserve your energy. And we really succeeded in that, designing those coefficients. They're non-linear, but not very much non-linear. Our optimizer gave us these results. At the end of the story, what we achieved, we tested our system against criteria, numbers that were given by Ingenuity helicopter. And the Ingenuity helicopter, we used a similar mass and similar numbers. And actually, what we have achieved, we achieved hovering of the vehicle that is comparable with the size and mass with the Ingenuity helicopter. We used a power of 95 watts for sustaining flight for our vehicle. And we know that Ingenuity helicopter consumes 350, so it's one third of power is saved. So we use only one third of power comparing to helicopter. Okay, of course these are not the final numbers. You have a different another losses in a gearbox, etc. So this is not a. I mean, I do not claim that we have a 3 times better power efficiency. However, it is a good good sign that we can achieve some advantages by going through this perspective. You have to add some other noises. You know that very well. However, 3 times are pretty big difference. So, my friends, this is my group. Of course, you cannot do this by yourself. So this is my main colleagues in Zagreb. I have some more colleagues, but these are main colleagues, and these are my colleagues from Politecnico di Milano, Professor Maserati, and from TU Delft, Professor De Kroon. We just submitted another proposal to European Space Agency. I'm again a principal investigator. Now, based on these results, we will build hopefully we will build a prototype, and we will put it in the Mars chamber here in Europe, and to test all those ideas experimentally based on our simulations. So this is the last slide. I thank you for your attention.
Thank you so much, Zdravko. I think that was a really comprehensive coverage of a very challenging topic, and trying to fit it all within an hour, the extent of work that you have done. The floor is now open to questions, so any of the members of the audience, you may feel free to unmute yourself and ask. Those of you who are working on flapping wings, maybe you can ask Zdravko. It's a great opportunity for you to explore the cutting edge of what is being looked at, because flapping wing is quite challenging as you go to smaller sizes, even on Earth. Now we are talking of two extremes of Mars and Venus, as Zdravko showcased, and also his geometric approach,
I see some
which integrates.
Okay.
I
see a question in the chat. Have you experienced explode optimus for flexibility? You mean flexibility of wings? We have not done it yet numerically extensively. So one of our goal is now to expand our solver by putting elasticity of the wings. So far in this results, we used rigid wings. So it is really let's say it's not a completely realistic, but as I said, this is the point we start from. However, it's not a problem to implement elasticity effects, and of course we will do this in this very it's the next phase of the project. We will be building this in an experimental setting, and we will also put flexibility of the wings in a numerical setting. We used elasticity as elastic elements, however, only in joints. What I have shown. So we have implemented elasticity of the system, but in a discrete manner by putting in joints, not along the continuum. Right. I hope that I answered it. Have you considered of the plane considering the effect of surrounding flow conditions, gas and winds? Yes. Well, again in the future. We haven't done it so far. We would of course you'd have to do it. We have this idea, but please understand that how to say it. It's a challenging problem. So we have, if you want to build this prototype, and we are going to do that, we will start first from hovering. We will optimize our actuators and implement some control algorithms to have this guy airborne as we would like to have it. And then when all these things are solved, then we can start taking a look into wind gusts. This is the same thing as with helicopter. In Mars, you can have gusts, right? And the NASA, when they have this first flight, they actually pray to God that don't have a gust to demolish helicopter in the first flights. So you cannot solve everything. So gusts are something, of course, to cope with, and in the future you need to do that, but well, step by step, right? So these are two questions in chat.
Zdravko, there is one more question in the Q&A, which is next to the chat by Jana Ravikiran. He's asking, for the planets which do not have atmosphere, what solutions exist? So going to even more rarefied atmospheres than Mars.
Sorry, I don't see this question, but of course I hear you what you said.
That Q&A, yeah.
Here. Okay. Have you? Yeah. So
like
so
on
question,
your left. On your left pane,
yes,
you have that Q&A, yeah.
Yes. I see it, yes. For we do not have, oh yeah, of course, you cannot, if you don't have atmosphere, you cannot use your flapping wings, or you need to, for there you need to have a rocket propulsion or something like that, yeah. For example, if you want to design a drone on the moon, which is also something that is ongoing. I mean, agencies are looking at the problem. You need to have your actuators based on rocket propulsion, because you don't have an atmosphere, so you cannot use I mean, flying mechanisms, right? Atmospheric fly. You need to have a propulsion, rocket propulsion. Yeah? Okay. Do we have some more?
Yeah, I think there's one more on the Q&A on the top. Prashant Kumar Sahai. He asks, how have you modeled the wing best?
How can you model the wing beat? What does it mean, beat dynamics? Just a minute. Wing beat dynamic. Wing beat. I don't understand. What does it beat? Does it mean how to model a pattern or?
Nanjappa, maybe you could unmute and explain yourself. Yes, this is a new post. This is derivation of equations of motion.
Sorry.
I think
please, can you repeat?
Nanjappa, can you just explain what you mean by beat over there?
Yes.
He's a group captain from the Indian Air Force.
Engineer Force. I don't get it. I'm very sorry. I don't get it. What do you mean? We actually cooperate. If we confine ourselves on the rigid wing so far, as I already explained, we do have our elasticity in the joints, but and then we consider everything there. I mean, you have inertia forces, you have interaction with the fluid, so speaking of that, it's mathematics is completely set up. Everything was there. We made experiments with different wing inertias. We using the smaller inertias and bigger inertias in our experiments, numerical experiments, because we still do not know what kind of technology will be used for a production of wings. So we in the future we can have a heavier wings or lighter wings. So for this reason we changed this information. I'm speaking of inertia. We used the different numbers for inertia forces, for inertias to get different inertia forces. And then we did experiments with elasticity by using a different wing masses. However, we could have emulate, as I mentioned, the inertial forces with elastic elements quite successfully in both variations, with a lighter and with a heavier wings. Yeah, if this is what you mean by beat. Yeah. So please ask whatever you want. I mean, don't be inhibited. Well, we can chat. So.
Zdravko, I think if you go to Q&A and click on new post, there are a few posts on the top.
Yes, of course. Sorry. Q&A. I'm doing right now. Q&A. Yes.
On the top, there's something called new posts. So if you can click on
yes,
that.
My speaker is offline. Sorry. Okay. A criteria for deciding optimal flapping wing. Yeah. Okay. Thank you. Yeah, I see. Okay, criteria for designing optimal pattern. Criteria was first criteria was energy efficient hovering. So we set up our system, and we said, all right, now we have tried to find optimal flapping pattern, meaning optimal frequency, but however also optimal kinematics, right? So our optimizer is capable of finding the right kinematics with criteria to have minimum energy needed to sustain hover. All right. Of course, then you need to put as input what is your mass of your vehicle. You have some benefit from the point of view that on Mars you have a gravity that is 3 times lesser than here on Earth. So you have a better situation there. However, your aerodynamics is much more challenging, as I mentioned that, right? So you put your numbers. You said, right, I would like to have a hover of the, let's say, 200 grams or 500 grams machine. So please give me optimal pattern to sustain flight of this mass. All right. So this is the criteria. Criteria was the optimal energy consumption for hovering. All right. Super. Is Lagrangian or Hamiltonian used to come about of the? Yeah, this is also a good question. Well, both. How to say it? As you know, if you formulate a Hamiltonian system, meaning non-dissipative systems, then the both formulation actually gives you the same result. Yeah, it's only depending how you formulate equations of motion. However, for this DMOC approach, discrete mechanical optimal approach, it pays off to go to Hamiltonian approach, to do this Legendre transformation, to go to the Hamiltonian approach. It gives you some numerical benefits, right? So actually, for optimization purpose, we transfer ourselves from Lagrangian to Hamiltonian formulation. But we also did for first equation formulation, we also used a Lagrangian approach. However, Hamiltonian approach is a little bit more, how to say, since it's about the momenta. You live in a phase space. In a differential geometry, we call it, you live in a cotangent bundle. You have this momentum as a variable. It is a little bit better from the perspective of designing energy momentum conserving integration schemes, because, for example, if you want to design a scheme that conserves your angular momentum, and sometimes it pays off to do that, then in Hamiltonian system you have this right there as a variable, and you conserve this. You can have a quite good setting of equations for structure preserving scheme. It's called structure preserving scheme, right? These are numerical schemes that preserve certain first integral of the motion, preserve momentum or preserve energy. So if you do with the rigid bodies, then you can really design it also in the flexible bodies as well. But you can design schemes that can preserve your momenta, right? So Hamiltonian kingdom, let's say, or realm or domain, is a little bit more natural, right? It's also there are some people advocating Hamiltonian because of you can have if you have a different frequencies in the system, then it helps you with to improve numerics for different frequencies. So I would say generally Hamiltonian is a little bit better setting to work in from numerical perspective. However, speaking of analytical physics, of course, if you are doing things in a Hamiltonian non-conservative, you don't have dissipation, then the both solutions should be identical, right? But numerics, of course, is different. So this is the okay. So my speaker, criteria designing, I answered criteria, Lagrangian, Hamiltonian, I answered that. I published, if you're interested in these things, I published a structure preserving scheme, for example, for treating a rigid body. You can think of heavy top, because heavy top is very interesting. How to say, physical example, because you have a different momenta, different motion invariance you need to preserve. Momentum, you have energy, you have an angle between a kinetical momentum and an axis, blah, blah, there are different, I think 5 of them, they need to be preserved, so-called Casimirs, etc. And so you can actually design numerical scheme that preserve those things. My scheme, I preserve by default momentum and energy, meaning that actually you cannot spoil. You can have a integration step, whatever you would like to have, but you always have preserved those integrals of motion. This is a really interesting thing. So we have these things published. So kinetics, derivation of equation motion. Probably I answered that. As I speaking of a multi-body system, we started from Lagrangian approach. Actually, then we use Newton-Euler equations, not like Lagrangian equations. In a strict sense, people introduce independent coordinates, etc. So we do not use this. We start from Newton-Euler equations. So we have 6 equations for each body, right? Because we have a 6 degrees of freedom for each body, or naturally. So we have this. So however, speaking of rotations, we do not use 3 other angles or quaternions. Quaternions are also, probably you know that, are very, very, most popular parameterization of treating rotations are quaternions, because by using quaternions, you avoid gimbal lock that is inherent with the other angles. With the other angles, you should be very, very careful when you have a really 3D rotation, because you have these singularities, as you might know that. So people go for quaternions. NASA go for quaternions. I was there, I gave a talk there. So they're using quaternions. And however, I'm not using quaternions. I'm using rotation group SO3, because when you have a finite rotations, by default, you are living in, your space when you live is a SO3 group. It's not quaternion group. Quaternion is only parameterization of SO3 group. So SO3 group, Lie group, it's a natural. You live there. If you speak about translations, you live in a vectorial space. If you speak about rotations, you do live in a space of special orthogonal matrices, SO3 matrix, SO3 group. So this is your natural space you live in. And I calculating things directly in SO3 group. I do not need parameterizations like Euler angles or quaternions. Just don't need it. I have it directly in SO3 group. It does have some advantages to do that. Although quaternion is a very good representation, it avoids singularities. But as you might know, with with a unit length quaternions, because they are unit length, you need to have this stabilization step, because your quaternion should be of length 1 unit norm. So you need to have this constraint stabilization extra step to force it to be unit. And this is what I don't like. I don't like this enforcement of things. I'm much more interested when I can have mathematics that actually avoid these constraints, have an elegant, more, and SO3 group is the way to go, because there you have your result exactly when you want to have it, without any constraints and any extra effort. All right. Allow quaternion is very good. People use quaternions everywhere, and this extra step of stabilizing quaternion is a very efficient one. You just need to have one more equation. So it's really going to real life. It's quaternions is a good way to go, because this extra step is really not expensive. However, you need to do it, right? And there are some examples I know in my contacts with the people, that people actually just implement quaternions in the wrong way. They do not do this extra stabilization step, then meaning that in course of simulation they got erroneous results, because quaternion is spoiled, is not anymore a unit one. And it should be unit 1 if you want to represent rotations. So if you use if you live in an SO3 group, you have your matrices in machine precision, because Lie group integrator gives you updates in SO3 group by having this SO3 propositions in a machine precision manner, right? So this is our approach. This Lie group approach. So as I mentioned, we derive our equations of motion directly by using SO3 for geometric nonlinearities. And then, as you know very well, for finite elements with a larger formation, it's always the case how you treat your finite rotations. Do you have some approximation? How do you do this? Is it the good one or bad one? So there are different advocates for different procedures. And in my case, I have a let's say a result correct by definition. All right. Yeah. I answered that. So just a minute. I answered that. Speaker offline. Criteria: flopping green, Lagrange Hamiltonian, kinetics, derivation is a motion. How you model the twin big dynamics? You have export optimal space for. Oh yeah, yeah. I believe I answered all those. So this is something else. Just a minute. What is this? Have you yeah, this is, have you treated vortices 11 tab? Good question. Yes, you need to have this question is from someone who knows flapping wing. You have also leading edge but trailing edge vortices, exactly. Yes, we treat them. We treat them. For this, speaking of fluid, we basically, when go to the background, what we did this Helmholtz-Hodge decomposition of the fluid flow. So we have a Laplacian flow and we have divergence-free flow because it's incompressible. So Laplacian flow we solve by reducing it everything on a solid, as I mentioned, by using this symplectic reduction. What I mentioned in my talk, this relabeling particle relabeling symmetry is a cotangent bundle. It's a symplectic reduction of the system, right? By using this symplectic reduction, we reduced everything on a solid, and fluid vanishes out from equations of motion. It's incorporating only by Eden-Nest's effect. and which is of course very important because you have a large accelerations. This is the specifics of the flapping wing, because you have a very complicated kinematics and you have a large acceleration. So added mass effect is significant there. You don't this mass effect is not that significant in a fixed wing, because it's you don't. But in the flapping wing, it's a very significant. So by this symplectic reduction, we actually solved added mass problem. We don't need to do discretization of the whole fluid, because we reduce everything on a solid. But however, of course, added mass is changing because of velocity, so you have to update your added mass frequently, yeah, because it's changing all the time, right? So this is for a Laplacian part of the flow. This vortex wake, but apart from that, you need to treat wakes. You have a leading edge and trailing edge vortices. Here in the flapping wing, a leading edge vortice is an important one, but of course you have a trailing edge vortices as well. So how we did it, because we were not interested in high fidelity, because this is not for use order modeling, you don't need that. So we actually used unsteady vortex method. So for vortices, we shed vortices from the both sides, as you ask, from the both sides, and we used UVLM, unsteady vortex lattice. So we use this nothing new in this part. Therefore I have not devoted my time explaining this, because this is just standard vortex wake method for treating those things. However, you have to treat lead and as you mentioned, with the both sides. So then you have your criteria when your leading edge vortex will also be shed apart from the trailing edge. So you have to incorporate this criteria. So we there are some papers on that problem. So we used information given from the literature. Speaking of trailing, but also leading edge vortices, you have to determine frequency of the how in which frequency you will shed your vortices. This is important feature, and because the whole system is not posed mathematically that you can have only one solution. You have to incorporate some more criteria to solve the whole thing. And for this reason, we use this, what I mentioned in my talk, this Strohal number. I came up with this idea. An idea is rooted in this physical fact that we observed by studying flapping systems in air or in aqua. We observed that actually the both guys, to have an optimal propulsion, they use a very similar Strohal number in certain range, right? So this means that from this Strohal number you can come up with a frequency of the trailing edges of the vortices. Then we started from this idea. And then we tuned our solver. For numerics to based on this Strohal number. So we did have some initial idea how should we shed our vortices if we would like to have a optimal propulsion. If you don't have this idea, then people do this by rule and thumb. People just say, okay, I will shed my next vortex in the half distance from the last one. They have different criteria. External criteria, put it this way. For our purpose, because we have this propulsion thing, I decided to incorporate this Strohal number criteria for also to tune my numerics, right? I'm advocate of these things to use the symmetries, because this is some kind of symmetry, and our universe is full of symmetries. As you might know, conservation energy or momentum conservation. This is only symmetry of the system. It has consequence in the mathematical sense of Noether theorem. Amy Noether is a mathematician lady. Yeah? She came up with this theorem saying that every time the system, with Hamiltonian of the system is not changing when Lie groups acting up to the system, then momentum up is conserved, so-called momentum up. And momentum up is those conservation laws. So all those conservation laws actually are a consequence of the symmetry of the system. So it's fantastic, and we can explore the symmetries with the idea of reducing our mathematics. So instead of discretizing everything, this is what people do. They say, well, I don't care. I will discretize my continuum by using finite volumes or elements. I will discretize this guy. I will put everything into machine, and then I will wait up to the result. Yeah, okay, you can do that, but is this the most smartest way to do? I doubt so, because your machine does not know many things about universe. For example, it's a very simple equation. Just try to integrate your spinning top, or integrate just integrate a pendulum. And if you don't have a structure preserving scheme, you will violate your energy. I mean, you will violate it, and because your mathematical algorithm, whatever Runge-Kutta, which is only I think astable. It's not depends on the different schemes, but definitely you will not capture dynamics without problems, because you will have your fourth order scheme, but you will violate your energy, you will violate your momentum, because your mathematical algorithm does not anything about your energy, right? So you need to have a smart integrator that will take care of this symmetry. Therefore, you need to put it in your mathematical scheme. Yeah, otherwise you cannot do it. And this is what we also came up with some solutions. So this is what I'm aiming to, not discretize everything and pray to God that everything is fine. No, think about things, find your symmetries, do your analytics as much as you can, and then implement your numerics only there where you cannot have your things analytically solved. Of course, then you can also use artificial intelligence. Let's call this. I mean, today everything is artificial intelligence, but you can use your learning algorithm to because sometimes our models are just not accurate enough. So you need to have you can have your data, and you can have this hybrid, let's say, approach, having everything. I mean, a little bit more statistics, a little bit more model, and get all the things together. However, using symmetries and take advantage of symmetries of systems is important way of doing if you want to have it accurately. Yeah. There is some more question here. Thank you very much. Thank you for your question. But there is something else here.
Zdravko, on chat window, there's one last question on the criteria for deciding optimal pattern of flapping wing.
Just a minute, I have to find it.
Yeah, it's not in Q&A, but the chat window.
Here's the chat window. Just a minute.
At the bottom of it.
Sorry. I don't see it.
I think he's just asking for the criteria.
Yeah. I just a minute. Yes. There's some more. Just a minute. Have you explored? But there's something else. Have you explored optimal particle? Yes. Have you considered the surrounding fluid gas? I answered gas and winds. I answered. Yes, we can do this, but this is something to do in the future. Thank you for answering. I work on the Air Force. These are very yes for being yeah. Well, of course, Dinesh, please share my email address so everybody can reach me also via email, and we can share some some papers, etc. Criteria for deciding optimal pattern of flapping wing. I said that our criteria was to find a flapping pattern that will satisfy this minimum energy criteria. So our basic, let's say, our basic criteria was to find a most efficient way to hover. Why just hover? Because hover is very complex. Because for hovering, you don't have a horizontal velocity. Your fixed wing cannot hover. Yeah, it falls down like a brick, right? If you don't have a horizontal velocity. So also this hummingbird is the only bird that can hover. Because it's very high frequency of the you can see this video somewhere. I mean, but these guys, it's a very energy consumption for hovering is very high. So these guys have to have to feed themselves very frequently to sustain themselves in a hovering way, because you actually stay afloat in a one position. So it's energy from energy point of view, it's very demanding, right? So therefore we said to ourselves, all right, let's find criteria to sustain hovering with a minimum power consumption. This was our criteria, and our optimizer find patterns that actually minimizes energy for this criteria. Okay.
Thank you very much, Zdravko. I think you took a lot of your time, not only for the presentation, but also in addressing every one of the questions. I think really helped a lot of these students, especially those working on this field in this area in flapping wings. So I will definitely, as you advised, share the email address, your email address with the audience so that they can directly approach you if they need to. And we hope to have you soon once again, whenever it is feasible for you.
It will be my pleasure. Thank you, Danesh, very much for hosting this talk. I hope that it was a interesting talk for you. We are doing this flapping wing research also. I mean, we are continuing with this. As I mentioned, now we are planning to build a prototype to go to Mars chamber to test everything there. My strong interest also lies in these mathematical models and anomaly groups in nonlinear spaces. I will share with you, I will send you an email. I'm organizing of one advanced PhD school. It's in Udine in Italy on geometric methods with my really distinguished friends. I will share this information with you. So please share it with your students and your colleagues. It will be in September this year. So registration is open. And beside myself, I will have 4 other professors, really experts in that field. So I was invited to give a keynote in Leuch. It's a center for physics in France. Actually, number of Nobel laureates gave a speech there. So these guys are very interesting. It's called geometric science information. So how to use this geometrical idea to treat data. Because you have a cloud of data, you can also find the symmetries there. It's a very interesting. So I'm also doing some work in that domain. So I will be in 1 month from now in April in France with my colleagues of mine working on these ideas. So there are different aspects of how you can use these symmetries in the universe, also for treating the data. So I will share it with you. So if there are some people who are interested in that things, I will be glad to talk to you again. So it's of course we can set up another meeting. I know when we go to differential geometry, to Lie groups, and these are not straightforward topics. I mean, you have to invest your time to studying it. I did it myself. So you cannot have it just so. For example, this course in Udine, I will be also providing some background for this kind of setting. I also can do this for you. I mean, but this cannot be one lecture. I have to introduce, Lie groups to give a proper mathematical framework, and then to understand, to explain the symmetries and these things. But those are really interesting. Things from my point of view, and as I see it, I think that I can claim it quite safely. This is the, let's say, future, because vector space, we know vector space very well. However, we do not live in linear spaces. We live in nonlinear space, as you know very well. So we have to explore this nonlinearity more, let's say, more scrutinizing what's going on. And then also in data science, but also mechanics, this setting, geometric setting, gives you a good environment to work in. Right?
Absolutely, can't agree with you more on that, because from our point of view, we work mostly on composite structural mechanics at my lab. And there also we've seen that there's been, over the years, at least in the last few decades, more emphasis on materials rather than geometry. And when you bring in geometry, the kind of optimization that you can do is to the next level, because it helps us to take things in a much more holistic view, as though repeating that particular word, but I think it's the idea of getting rid of boundaries and a seamless expansion of the possibilities. I think that came across very well when you also talked about not considering fluids and solids separately and trying to have a unified framework for both of them. I think that's the direction in which we have to head. There was a point of time when each of these fields was not so well understood, so it was important to dig deeper. Now that there is a reasonably broad understanding of many of these fields, in combining them and trying to see how things happen in reality, I think we do need to take advantage of things that we have not taken advantage of so far. And there, the geometric approach does play a very critical role indeed. And I can see the same thing, that what you're saying from a different point of view, from a different perspective. And it'll be really nice to continue this dialogue in some manner as we go forward. I definitely also pass on the information on the PhD school that you're doing at Udine, along with your colleagues, once you share that information with me.
Thank you very much. I will be really glad to do that. And just to mention, since you guys are going to Mars, Croatia does not go to Mars, but you guys you landed on Moon. My congratulations, really. And you landed on the dark side of the Moon. Let's say dark side. It's the far side, not dark, but far side. So really, yeah, it's really amazing. It's as far as I know, you are second. China did it a few years back, and you are second, as far as I know. Okay, and now I go. So please consider my flappers for your next Mars trip, right?
Thank you so much. Yeah, I don't think the Chinese were successful in their southern landing, so they did it later. So ours was the first.
Okay.
So that's really nice. And in fact, I think we started this talk today by talking about the East versus West, and then you said that you're a global citizen, which is so beautiful. But then I think you went even broader, looking at the inner planets and outer planets, Mars and Venus, and the whole galaxy. And then you talked about the symmetries and the universal laws associated with symmetries. I think that's so beautiful in understanding everything from a much more deeper philosophical point of view, because that's what is the underlying reality. So I'm so glad that we could have this dialogue.
So we are citizens of universe. This is
absolutely,
the right
absolutely. No doubt
completely.
about it.
Yes. Well, just what. So if you consider to fly on Mars, do not use helicopter. Go for a more.
However ingenious it might be.
Yeah. Thank you
And
very
though
much.
we are from Georgia Tech, many of us. I'm glad you brought out so many of those points we could relate to. Thank you so much, Zdravko.
Yeah, it was my pleasure, Dinesh, really, really. Yeah.
Take care and bye-bye.
Oh, thank you. Goodbye. Goodbye.
Bye-bye.
Bye.
See you.